Today's lab is about understanding how a capacitor charges and discharges in a simple RC circuit. A capacitor is a device that stores electrical energy in an electric field. When connected to a power source, it charges up quickly at first, then the rate slows down until it reaches its maximum voltage. When the source is removed, it discharges in the same exponential way. The key idea we're studying is the time constant, represented by the Greek letter tau. Tau. The time constant is the product of the resistance R and the capacitance C, written as tau equals R times C. It tells us how long it takes for the capacitor to reach about 63% of its full charge during charging or drop to 37% during discharging. In this lab, we'll use Capstone software to generate a square wave signal that repeatedly charges and discharges the capacitor. We'll record the voltage across the capacitor and observe how it changes over time. First, we'll measure and analyze the behavior of a single capacitor. Then, we'll connect two capacitors in parallel to see how the total capacitance changes and how that affects the charging time. By the end of the lab, we should understand how the time constant relates to resistance and capacitance, and how real measurements compare to theoretical predictions. Today we're going to need the following materials for our RC Circuit Lab. First, we'll use the Capstone software with its signal generator to produce our square wave voltage. We'll also use the voltage current sensor to record the capacitors voltage over time. Next, we'll need a circuit tablet or breadboard to connect all of our components. The components include one resistor of 10 ohms, one capacitor of 330 microfarads, a second capacitor of the same type for the parallel circuit setup, several connecting wires to complete the circuit and jump the coil on the tablet, and a power supply provided by the signal generator. That's everything we need. The signal generator, voltage sensor, resistor, capacitors, and connecting leads to observe how the capacitor charges and discharges in the RC circuit. First, we open Capstone and set the signal generator to a positive square wave with a 1 Hz frequency and 5 V amplitude. We also set the recording to stop automatically after 3 seconds and increase the sampling rate to 500 Hz. Next, we build the circuit using the signal generator, a 10 ohm resistor, and a 330 microfarad capacitor in series. On the circuit tablet, we jump the coil with a wire so current skips it. The voltage sensor is connected across the capacitor. We start by running the setup with one capacitor. We record one full charge and discharge cycle, then use the graph to find the times when the voltage is 0, V, and when it reaches 63% of the maximum. The difference gives the time constant, tau. From that, we calculate the experimental capacitance and percent error. Then we repeat the process with two capacitors in parallel, measuring and comparing the new time, constant and capacitance to theoretical values. Finally, we analyze results, compare percent errors, discuss possible sources of error, and write our reflections in the lab report.
Hello, my name is Said Gregorio Canton, and today I will go over lab number 6, which involves charging and discharging a capacitor. This is the data analysis. For this lab, we have to set up this circuit over here, and we will have to test two setups. One in which we test one capacitor, and a graph would show the time and the voltage that is read with this testing equipment over here. The other setup involves two capacitors in parallel, and we will likewise read the voltage over time. Our predictions and expectations of this is that it will behave like many other capacitors, in which the charging and discharging is speedy, exponential, and then becomes stabilized, steady afterwards. This is the graph for the capacitor by itself. As you can see, here is the voltage 0 at this time, then 63% charged at this other time, 0.5 seconds, the voltage reading, and the graph. Reading the circuit information, we find out that the capacitor had 100 microfarads capacitance, and the resistor was 10 ohms. We use this for the calculations. Likewise, using the difference between time 1 and time 2 to calculate our experimental capacitance, we see that the values are extremely off, giving us an 8,000% error. This is likely caused because of how the graph was set up. We see that it was rather linear instead of the exponential charging or growth in the voltage. This is likely the cause of such a percent error. Second setup, we have two capacitors set up in parallel. This is a graph that came with the reading. We see the voltage at 0 at this time, and then the voltage at 63% of being completely charged. The formula to calculate the total capacitance of two capacitors placed in parallel is just adding them up. We see that the 100 microfarads and 330 microfarads gives us a total of 430 microfarads. This, when compared with the experimental capacitance, using the difference in time 1 and time 2, gives us a pretty large percent error, 179%. This, when compared with the other procedure, gives us less percent error, considerably less, but still noticeable. This is likely caused by the same error that struck the last setup, which was that the previous graph, the graph for the parallel capacitors, seemed rather linear, not exponential, as is to be expected when reading how a capacitor behaves. That would be everything for the data analysis. Thank you for watching.
In this lab, we studied the charging and discharging process of capacitors in RC circuits and explored how resistance, capacitance, and circuit configurations affected the time constant tau. Using the relationship tau equals R times C, we measured the time it took for the capacitor to reach approximately 63% of its maximum charge and compared our experimental results to theoretical values. We also examined the behavior of capacitors connected in series and parallel, noting how each setup influenced total capacitance and the rate of charge and discharge. While our overall results followed the expected trends, our percent errors were significantly higher than normal, with single capacitors reaching around 8,000 percentage error and parallel configuration about 179%. These large discrepancies likely stemmed from a high speed of the charging and discharging process, where even small inaccuracies in identifying the 63% voltage point causes major deviation in the calculated time constant. The sampling rate of 500 Hz may not have even been fast enough to capture the rapid voltage changes accurately, leading to timing errors. Additionally, internal resistance in the capacitor, stray capacitance in connecting wires, and small connection imperfections could have altered the voltage behaved during each trial. Environmental factors such as temperature, humidity, and electrical noise in this lab might have also influenced our readings. Despite these errors, the experiment successfully demonstrated the key concept of capacitors charging and discharging and time constants in RC circuits. It also emphasizes how sensitive these systems are to the timing precision and experimental setups, showing that even small variations can lead to large percentage differences when compared to theoretical predictions.
Credits: Introduction, Geomaterials and Procedures, Pedro Data Analysis, Seath Conclusion, Aaron.